Yep.
Okay, so
Go.
today we're moving on to something a bit different. So far, everyone has been pretending that they're doing all of mathematics by themselves. Today, it's time to join the rest of the world. The lectures from now on are about explaining how math actually gets done in MATLAB and how to use what's in MATLAB. And Kevin is going to start us off telling us about order structures, things like inequalities and lattices, and interesting things like Galois insertions. Take it away, Kevin.
Hello, everyone. Sorry I'm late. I've only just finished. In fact, I should say I've committed the cardinal sin. My solutions file still has sorries in, which means, of course, now I'm a paranoid computer scientist. It means that there might actually be mistakes in the questions, but I think we're okay. So just to be warned, we're all right down to the very bottom. I'll get to that later. So what I learned when I became a computer scientist, or whatever I am now, is that when we give courses called groups, rings, and fields, computer scientists call this the algebra hierarchy. And yesterday, so I talked a bit about the algebra hierarchy yesterday, and Alex talked about the topology hierarchy. And then there's this other hierarchy called the order hierarchy, which, as a number theorist, I haven't really seen much of. I saw the concept of a partial order and a total order, but there's plenty more things beyond that. So this is just a very brief introduction into Lean's order hierarchy. So it starts with partially ordered sets, and then it goes on to things called lattices, and semi-lattices and lattices and complete lattices. So I was told to say something about the order hierarchy. So in some sense, my talk and then Alex's talk and now my next talk, explaining these three hierarchies. But now so basically I have to come up with some kind of type that I want to demonstrate is a kind of a cool element of the order hierarchy. And so I'm going to go with subgroups of a group because I think bundled subgroup, independent of the order hierarchy, there's another important thing, which is understanding how Lean does things like subgroups. And I should say that, in fact, the way subgroups are done has been changed in the last year or so. We used to define, we had a predicate on subsets called isSubgroup, which was a class, and we decided we didn't like that. And we moved over to a bundled approach, and we bundled subgroups. And in fact, the library still hasn't been completely switched over to these bundled subgroups. And so let me tell you what a bundled subgroup is. What's going on here? So here, unfortunately, subgroups have been already defined in Lean. So I'm going to talk about subgroups, but I'm going to call them subgroup, sort of typical mathematician abbreviation. So instead of using, if you kind of do some imports, then this file might break if I called it subgroup. So instead of working with a namespace, because I find it a bit of a hassle, I'm going to define subgroup. So let's have a look at the definition of the type of subgroups of a group. So this says let G be a group. And now we're going to make a new, the idea is, we're going to make the set of all subgroups of G. That's the idea. So a term of type subgroup G is going to be what? What is a subgroup of G? Well, of course, it's a subset of G. And remember, set G is Lean's, this is a little bit unfortunate. Set G should really be called subset G. If this was called subset G, it would be easy to understand. So set G is the type of subsets of G. So this first line says, let carrier be a subset of G. Okay, that's what, that's one of the fields we need for this structure. We need a subset of G, and then we need to put the axioms that say that this subset is a subgroup. And there's one axiom per piece of structure for a group. Like, what does it mean to be a subgroup? It means closed under all of these things here, right? It has to be closed under multiplication. So if A and B are in the carrier, then A times B is in the carrier. It has to be closed under the identity, by which I mean that the identity is in the carrier. And it has to be closed under inverses, i.e. if A is in the carrier, then A inverse is in the carrier. So that's the definition of the type of subgroups of G. And so now a term of type subgroup G is a subgroup of G. That's what we could say informally. And more formally, we could say that to give a term of type subgroup G, we have to give a subset of G called the carrier, and then we have to prove these three axioms. So that's how subgroups of G are done that's how bundled subgroups of G are done. The reason it's bundled is because the carrier is part of the structure. You see groups, anyway, the carrier is part of the structure. That's what bundled means. And this carrier thing, as a mathematician, you kind of, you forget, right? You say, let H be a subgroup of G, and then you talk about H as being a set, because H is a set that satisfies some axioms. Because we've bundled everything, if H has type subgroup G, then H isn't actually a set, right? H is a quadruple. H is 4 things. It's a set and 3 proofs. And so we're thinking about this very carefully. You see, we have this function now, subgroup carrier, and that function there, this field of this structure, takes a term of type subgroup G and returns a term of type set G. So it's like, this is a functor, right? This is a functor from subgroups of G to subsets of G. So we'll be seeing this carrier. We will carefully distinguish the subgroup from the subset, and it will be helpful. So we've got this subgroup dot carrier that takes a subgroup of G and returns the underlying subset. So variables, let G be a group, and let H, J, and K be subgroups, and let A, B, and C be elements of G, just because why not? So when you make a new structure, one of the first things you tend to prove about it, in fact, often the first thing you tend to prove about it, is an extensionality lemma for that structure. So what does that mean in this case? The idea is, given 2 subgroups of G, we need to figure out a nice way of figuring out that they're equal. So here's our first lemma, and I've proved it for you because it's sort of messy and fiddly, but not difficult. Our first lemma is that if H and J are subgroups of G, and they have the same carrier, i.e. the same subset, then they're the same subgroup. So this is obvious because if you take H and J apart, you realize that actually H and J are carriers, they're nothing more than carriers together with some axioms, and 2 proofs of the same theorem are by definition the same proof. So the simplifier just kind of deals with this problem instantly. So this is the statement that the carrier, this says for all H and J, if H dot carrier equals J dot carrier, then H equals J. And if you think about it, that's exactly the statement that the carrier function is injective. So that's an extensionality lemma. It tells us a way to prove that 2 subgroups are equal. But in fact, there's a slightly better extensionality lemma that we can't quite see. Let me put it down there. It says that to prove that 2 subgroups are equal, it suffices to prove they have the same element, that the underlying subsets have the same elements. And so how are we going to prove this? We've got to prove that 2 subgroups are equal. If we apply injectivity of carrier, we now have to just prove that the 2 subsets are equal. The two subsets are equal. And so now we can use extensionality for subsets when 2 sets equal when they have the same elements. So I'm using the ext tactic to reduce us to the question that says they have the same elements. So again, that's a slightly fiddly proof. I'm also looking at the wrong file. Why don't I look at the exercises file rather than telling you all the answers? There we go. So I did those 2 exercises for you, but here's one you can do yourself. Now, I've done the hard way. Why don't you prove that 2 subgroups are equal if and only if the underlying subsets have got the same elements? So that's an if and only if, so you can split it, and one way is the way I've just done, and the other way is easy. So there's a basic introduction. So that's how we're going to do subgroups. And why have I set up the theory of subgroups? Because I'm now going to show you how to put I'm going to put some order structures on this subgroup. And the first natural thing to put on this type of subgroups is to show that they're a partial order, right? How do we partially order subgroups? We just partially order subgroups by saying, we can look at inclusions of the underlying subsets, right? That's a very natural way to order subgroups. So H is less than or equal to J if and only if the carrier of H is a subset of the carrier of J. So this is a notation type class. We'll define an has LE instance on the type of subgroups, which is just a way of saying, we're defining H less than or equal to J, and we're defining it exactly by saying H dot carrier is a subset of G dot carrier. So now Scott introduced me this morning, and so I'll showcase some of his work. How do we know that, partial order isn't just a less than or equal to, right? It's got to satisfy 3 axioms. So here's Scott's tidy tactic, proving all of these axioms. Each of these axioms is not difficult. You just follow your nose. But in fact, the tidy tactic will do it for you. Because really, it's a question about sets And by extensionality of sets, it becomes a question about logic. It becomes a logical question, right? Like LE-REFL boils down to the statement that P if and only if P, and LE-TRANS boils down to the statement that if P implies Q and Q implies R, then P implies R. And LE-ANTISYM says if P implies Q and Q implies P, then P if and only if Q. So the tidy tactic does all of those things. So there's a nice automated proof that subgroups are a partial order. And here's another proof. There's a partial order dot lift function that says if I have an injection from A to B and B is partially ordered, then A inherits a partial order. So our subgroup dot carrier function here, that's it. We proved it was an injective function, and so we can feed that function and the proof that it's injective into the partial order dot lift function, and that gives us another proof that G is a partial order. I figure that the people in the audience understand what partial orders are, so I haven't made too much of a meal of partial orders. But now I'll be more, now let's go on to lattices, and I'll say, I'll be more careful about what a lattice is. So we're going to define some lattice structures on subgroup G, and lattices extend partial orders. And I'm going to give a very simple example of a lattice first. I'm going to give one of the most simple examples, and then essentially the most complicated example. So a semi-lattice inf top is a partial order with two extra pieces of structure. It's a partial order with an inf, i.e., you can take the intersection of two subgroups and you get a subgroup. And there's a top as well, and the top is the biggest subgroup. So these are two random, in general, a semi-lattice inf top is a partial order together with some way of taking an inf of two elements and some way of taking a top element. And then it satisfies some axioms. I'll show you the axioms later. It's pretty easy to guess what the axioms are. So now our job is to define inf and top for subgroups. So here's our definition of top. Our definition of top, that's supposed to be the biggest subgroup of G. And so what's its carrier? Its carrier is the biggest subset of G, which is, as mathematicians, we call it G, but because sets are not the same as types, in Lean we call it univ, right? Univ, set.univ, this is just G, right? This is just G considered as a subset of G. There. So set.univ is the subset, but now, of course, we've got to prove that this subset is a subgroup, so we've got to check the axioms. So I leave that to you. And of course, this boils down to knowing how to prove that every element of G is in G. And so I'm going to, I'm making the interface for subgroups, but I'm assuming, let's just assume that we have the interface for subsets. So mem univ G is the theorem in Lean's set library that says that every element of G is in the universal subset. So that's how we make top. And now here's some type class notation. This is a notational type class has top. You see, we can now do, look, we can do check top. There, subgroup G. There, that doesn't give us an error. And if we'd done it just before here we get an error. You see, there's the red underline. I've noticed, actually, talking to people, a lot of people are staring at the kind of chaos over here. There's a fancy new thing here. There's lots and lots of output here. And people are saying, oh, do I have an error? There's something over here. I'm always looking over here. Look, there's my little red underline. That red underline says there's a problem. If I put it down here, there's no red underline, and so there's no problem. So now we have this /top notation, this fancy logic notation for the biggest subgroup of G. And now we have to define inf, right? Let's define the inf of two subgroups of G, and that's a subgroup of G. And the underlying carrier is just their intersection, right? What I'm doing is I'm proving the quotes theorem that the intersection of two subgroups is a subgroup. But actually,
can I ask a question about the red underline?
Yeah.
Maybe it's because I'm old, but I find it incredibly hard to see red underlines, especially when the underline is under a dot or something tiny.
Yeah.
Well, it's minuscule. Why don't you replace red underline with something like a highlight or something you can actually see?
Oh, that's interesting. So there's a bunch of people that are very good at things like that. You see, I know my way around the info view. You see, I can fold things and unfold things.
As something you could configure instead of a squiggle.
Yeah. This is
also
exactly...
anything in which color is trying to convey information is useless for your users who are red-green colorblind.
Yeah, that's
And
interesting.
then
Yeah,
I can see there's an underline of that word definition.
Definition is underlined in orange,
Well,
which
I couldn't
means that there's
possibly
a
tell you
sorry.
whether that was orange or green or anything else.
John,
So
this is a great point. This
if
is
the
a great
color
point.
matters, then please don't use color.
Yeah.
Thanks.
So this orange underline means you've cheated, you've used a sorry, and that red underline we had above that was very difficult to see, I certainly grant, means you have an error.
Should I also ask a question? Oh, sorry.
Go ahead.
So who's first?
You go ahead, Luke.
Okay, so how is a subgroup of a group here a group? G is...
we didn't prove that. Yeah,
okay.
that's something that we should... I don't get round to proving that.
Maybe
that's certainly something you need to prove.
Like,
but there's a catch, right? Because a group is a type and a subgroup is a term.
Exactly.
Right? H colon subgroup G is a term, and so you're going to have to coerce that subgroup to a type, and so you can do that with something called has co-e to sort. Yeah, you have to coerce. This is saying a subgroup is a group. In some sense, it doesn't make sense because you're at the wrong level of the hierarchy. You have universes, types, and terms, and H is a term, but to give a group structure on H, you need H to be a type.
But I missed how the data of the multiplication in G is contained in a subgroup, because it just contains G as a set, right?
H is a subset. Yeah. Well, let's call it. I mean, we could call it carrier. We could call it H. H is a subset of G, and then this multiplication is G's multiplication, right? A and B are in G, and the axiom says that if A happens to be an H and if B happens to be an H, then A times B must also be an H.
Yes, but that's just a proof of that fact. But actually,
that's
the
right.
data of the multiplication itself is forgotten, right? Or
there is only one multiplication, and it's the multiplication on G.
Okay,
This here is the multiplication on G. We have not defined a multiplication on H. H is inheriting the multiplication on G.
Okay, but if I have a specific subgroup and then it still remembers this multiplication in G.
It remembers G, and then the type class inference systems remembers the multiplication in G.
Okay, thanks.
Was there another question?
So my question was, when you defined subgroup, you used structure, and I was just wondering why you didn't use class.
If I used class, then every group would only be allowed to have one subgroup. Otherwise, there would be diamond issues.
All right.
I use class for group because given a set or a type, I only really want to put one group structure on it usually. But given a group, I typically want many subgroups.
And classes would mean that you want Lin to guess a subgroup of G as soon as you give him G. So that's just simply not what classes are measuring.
I see, right, okay.
Yeah, this is a great example of a structure that isn't a class.
Compare it, for example, to the natural numbers or the integers. On the integers, we only want to consider exactly one additive group structure. And hence, we can do that using the type class system. So
yeah, so group is a class, but the integers themselves are not a class because we want to consider more than one integer.
Right, yeah, okay. Yeah, that makes sense.
So I've made subgroups a structure, but not a class. So you might think that the intersection of two...
I'm sorry.
You might think that... Sorry, was there a question?
Yes, I have a question. Why don't we define subgroup to be grouped together with the injective morphism?
Oh yeah, we could totally do that. Yeah.
Maybe
in fact, in the category theory library, I would imagine that that's how it's done.
I guess that will simplify the issues about making it back into a type.
Yeah. It will just, this is, you, as mathematicians, we have to be very careful when we're saying, you've done this implementation, why don't we do another implementation? There are pros and cons to every implementation. We, as mathematicians, we have a specification. We know exactly what a subgroup of G is, and we have 10 ways of thinking about it, and we switch freely between those ways. But we have to choose an implementation, and this is the implementation that's been chosen in MathLib. So the answer to your question is, it will make some things easier and some things harder if we did it a different way.
I see, thank you.
But because I'm not even supposed to be talking about subgroups, I'm supposed to be talking about lattice structures. So this looks like a theorem to mathematicians. It says the intersection of two subgroups is a subgroup. But in fact, in Lean, it's a definition, right? This is a definition of the inf function that takes two subgroups in and spits out another subgroup. So the underlying subset is the intersection of the two subsets. And now we have to prove that the intersection of two subgroups is closed under multiplication 1 and inverse. And I've left that to you. And again, just like top, we have some weird computer science notation for top. We've got some weird computer science notation for inf. /inf gives us this exciting thing that looks a bit like intersection, but is a lot squarer. And this is a notation type class for hasinf. So now we can start talking about if H and K are two subgroups, we won't write H intersect K, the normal intersection, because we're not working with subsets. We're working with lattices. So we're going to use lattice notation. So we've defined inf and top, and now there's 4 lemmas to prove. And you might be able to, so the axioms for a semi-lattice inf top are these 4 axioms here. And you might be able to guess what these axioms say. Le top says, given any subgroup is less than or equal to the top subgroup, right? So that actually says any, that follows from the fact that any subset of G is a subset of G. And inf Le left says H inf K is less than or equal to H, which really just says, it says by definition this. I've proved this one for you. I've shown you one way of doing it. The question is this, but by definition, it just means that, right? That if you unravel all these definitions, definition of less than or equal to and definition of inf, it just literally says H dot carrier intersect K dot carrier is a subset of H dot carrier. And now you can solve that with library search, right? If you don't know your way around if you don't know your way around the set interface, you see library search says, oh yeah, that's called inter subset left there. So I've applied inter subset left. And you might now be able to guess how to prove inf Le right. Now we know that it's called inter subset left. And similarly here, the last axiom for a semi-lattice inf top is that if H is less than or equal to J and H is less than or equal to K, then H is less than or equal to the inf of J and K. So figure out what question that is about sets and figure out how to prove it. And now we've proved those 4 axioms, and now we can just make a semi-lattice inf top. You see, this is a class, right? We only want one instance of semi-lattice inf top on any subgroup. The idea is we're not suddenly going to decide that our partial order has got a new top element. Somehow, given a partial order, there's going to be exactly one top element. And so there's the proof that subgroups are a semi-lattice inf top. So in fact, we can do better than finite. We can do better than finite imps. We can do arbitrary imps, right? Given a collection, look at this. Now we have an entire collection of subgroups, right? S is a set of, now you can see that this set is really good. Using set instead of subset is a really good idea. S is now a set of subgroups of G. If S is a set of subgroups of G, I can make another subgroup of G, and all I do is I take the intersection. And in fact, I've cheated. What I've done is I've pushed this set of subgroups of G, I pushed it forward to a set of subsets of G, and I've taken their inf in the lattice of subsets of G. And so now you've got to prove, that the intersection of a collection of subgroups is a subgroup by proving the 3 axioms here. And I've told you the interface you need from the set theory, from the language of sets. So now we have an intersection, an arbitrary intersection of subsets, and now I may as well tell you about complete lattices. So I should say a lattice has an inf and a bot and a sup and a top for 2 elements, inf of 2 elements and sup of 2 elements. But a complete lattice has an inf and a bot and a sup and a top, where now we kind of capital inf. This is capital inf and little inf are different, right? Capital inf is the meat of 2 elements, and small inf is the meat of 2 elements, and capital inf is the meat of an arbitrary collection of elements. And so we've just defined a capital inf. Given a collection of subgroups of G, we can make a subgroup of G, which is somehow the biggest subgroup contained in all of them. And now there's a cheat. So I've done this, but Patrick told me about half an hour ago that I shouldn't have done it this way. So apologies. I've cheated. I can make a complete lattice immediately there's a constructor for complete lattices that just says all you have to do is define an inf, and then you have to actually prove that the inf is a greatest lower bound. So there's a proof here.
It's not where you cheated. You cheated in the next section.
Yeah. Okay, I'm not cheating here, but I'm cheating in the next section. So I'll explain while I'm cheating, and then I'll stop talking. So now here we've got to prove that given a collection of subgroups of G, I claim that their inf is actually the greatest lower bound. So that's, you know, we need to prove some lemma about infinite intersections. And so given an inf with this property, we instantly make a complete lattice. And a complete lattice is just what you think it is, right? It has arbitrary imps, it has arbitrary subs, and it satisfies some axioms. You know, it says X is at least inf X, you know, I don't know. It satisfies some tedious axioms that we're not going to go into. But now the last thing I want to tell you about is Galois connections and Galois insertions. So a Galois connection is just a pair of adjoint functors. That's the easiest way of defining it. So a partially ordered set is a category, right? Because the objects are the elements of the partially ordered set. And the Hom sets have got size at most 1. There's a map from H to J if and only if H is less than or equal to J. So you can think about any partially ordered set as a category. And you know, like for composition of morphisms is just transitivity. And the identity morphism is reflexivity. So we've got two partially ordered sets, alpha and beta, and then we have two functors from alpha to beta called L and U. And if these functors are adjoint, which says L of A is less than or equal to B, if and only if A is less than or equal to U of B, then this setup is called a Galois connection. So a Galois connection is a baby version of two adjoint functors when we're talking about partially ordered sets. And the examples of Galois connections that we as mathematicians have seen, you know, there's one in Galois theory, when you go from subgroups of a group, subgroups of the Galois group to subfields of the big field. And then there's an example in classical algebraic geometry where you have affine varieties, you know, the zeros of a collection of functions is an affine variety, and the functions vanishing on affine variety is an ideal. And so you can move between affine varieties and ideals. These are two very common Galois connections, but there's just a very general theory of Galois connections. And the Galois connections I want to talk about in the last 5 minutes of this talk one is when alpha is the subsets and beta is the subgroups. So then our two adjoint functors, one of them we've seen, it's the carrier, and the other way is the subgroup generated by. And then the other example is if X is a, that's not really right. If X is a type, X is a set there, and alpha is the collection of subsets of X, sets of subsets of X, and B is the topologies on X. Now, a topology on X is a collection of subsets satisfying some axioms. So given a topology, we can get a collection of subsets, but given a collection of subsets, we can make a topology by looking at the topology generated by these subsets. So there's a general theory of Galois connections, that we won't talk about. But one of the axioms for a Galois connection is not the fact that if you do L and then U, you end up back where you start. So a Galois insertion is a special kind of Galois connection where if you do L and then U, you end up back where you start. And in the examples we're talking about, this is true. If I have a subgroup of G and I look at the underlying subset, and then I look at the group generated by that subset, you can see that I get back to the subgroup I start with. So this is a special kind of adjoint pair where you do forget and then you do generate and you get the identity. And this is also true for topological spaces. If I've got a topology on X and then I forget it and just think of it as a collection of subsets, and then I look at the topology generated by those subsets, I get the topology I start with. So these are two examples of Galois insertions. And well, now I feel bad because I've cheated. You see, I should have defined this span properly. Given a random subset of G, I'm supposed to make a subgroup of G. And because I defined inf already, I can just cheat. And I can say the subgroup generated by that subset is just the intersection, is the intersection of all the subgroups, the inf of all the subgroups that contain that subset. So that gives me a cheating definition of span. And then here are some lemmas about this span, because the span is the adjoint functor, you see. And so here's the lemmas that prove that this is an adjoint functor. This is one part of the adjoint, and this is the other part of the adjointness. But in fact, it's even better. It's not a less than or equal to, it's an equality. So here we have a Galois insertion, and then having, you know, given us this Galois insert, if we have this Galois insertion, which we can prove by just, you know, inserting all these lemmas, we have a Galois insertion, and then magically from a Galois insertion, we can construct a complete lattice. So this is the point of Galois insertions, is if I insert my Galois insertion into some magic function, then it will lift a complete lattice structure on the subsets of G, which we're assuming, to a complete lattice structure on the subgroups of G. So that's that, but I feel bad about that. So let me talk a little bit more about the topological space example. So this is just copied from Alex's talk yesterday. This is Alex's definition of a topological space. And then I define the forgetful functor from the topological space to the collection of subsets, just to be the, I define the forgetful functor to be just remember the open sets. And now here's Alex's exercise that got people excited yesterday. Given a bunch of subsets, we can make a topological space using this generated open thing. Here's our generated from. Generate from, given a collection of subsets of X, we can make a topological space structure on X. So this you saw yesterday. And this you see is an honest definition of generate. We didn't cheat. We didn't take the intersection of all the topologies that contain our subsets. We've made a general, we've properly generated our subsets. And so here's a proof that topological space structures on X form a partial order. It's just the fact that it's just another easy thing. And now here's a very long exercise. Why don't you prove that these two functors, that generating a topological space from a collection of subsets, and then given a topological space structure, just forget about it and think about it as open sets. Prove that these two things are functors, prove that they're adjoint functors, and then check that we have a Galois insertion, and check that we get a complete lattice structure on topological spaces. So these exercises might be tricky, and I must confess I haven't actually done them, but hopefully they're not too difficult. And that's the end of that. Right, so yeah, go fill in the sorries, that's your job. Yeah, I spoke far too long, again, apologies.
Okay, so thanks, Kevin, for introducing us to these lattice structures.